So last time we started Hilbert's irreducibility theorem, which states that if f is irreducible, then when you randomly project it to two variables, any irreducible n-variate polynomial, if you project to two variables in a random way, then it will remain irreducible with high probability. So today we will prove this theorem. Recall that the first lemma which we will need is this polynomial identity lemma, which says that if you have an n-variate polynomial which is non-zero, then on random evaluations the probability of it becoming 0 is very low. Okay, to be precise, it is the degree divided by the sample space. We skip the proof. The proof is easy to give using induction on the number of variables. Second thing we needed is we'll assume that our multivariate polynomial has a key variable x and n other variables, we'll call them y1 to yn, and we'll assume that this is an almost monic polynomial, which means that if you look at it with respect to x, then the leading x monomial, its coefficient will be now a polynomial in y bar in the variables y1 to yn, and if you set them to 0, the coefficient will not vanish. Okay, so the leading coefficient mod y0 is non-zero. In other words, the degree of the polynomial f does not change when you set y1 to yn to 0. This almost monic property can be ensured quite easily given any polynomial. So what you can do is if your polynomial is not almost monic, then you can just shift the variables y1 to yn by a random point, and you can show by using this polynomial identity lemma that it will become almost monic. Also, we noted that factors of almost monic polynomials are themselves almost monic. So now gradually we will move towards the proof of Hilbert's irreducibility theorem. So in that direction, the next lemma that we will do is as follows. So if the derivative of f is non-zero and f is irreducible, then if you randomly evaluate f, the probability that it is square full this probability is small. This is less than 2d square divided by the size of the sample space. Okay, so assuming a non-vanishing derivative and irreducibility, we can show that random fixing of y bar keeps the polynomial square free. So the way we will show this is recall that square freeness or square fullness relates to the discriminant of f. So what is the discriminant? discriminant is defined as the resultant of f with the derivative with respect to x. Okay, so when you do that, then x gets eliminated and you get a polynomial in y1 to yn. That is called discriminant. So recall that by the properties of resultant, recall that f with y bar fixed to b bar is square full if and only if b bar is a root of the discriminant. Okay, so what this is saying is that the way to interpret it is that when you are fixing the variables y1 to yn, and if suppose your polynomial becomes square full, then this means that b bar that you have picked is a root of the discriminant r. And now you can invoke the polynomial identity lemma, which says that this is a very rare event. Okay, so first note that the resultant is non-zero. Why is it non-zero? It is non-zero because you have assumed that the derivative was non-zero. Okay, so and f obviously is non-zero, so then the resultant is non-zero. Both of them, f depends on x actually, and it's almost monic. So the discriminant is non-zero because of almost monic and derivative non-zero. Okay, so because of these two properties, you can check that that R will be non-zero. So R is a non-zero polynomial R is non-zero and its degree is less than 2d square. Right? That is again property of the resultant. It says below 2d square actually. So then by the polynomial identity lemma, what you can deduce is probability if you pick b bar from S to the n space, then R b bar being 0 or b bar being a root of R, this is a low probability event, it's 2d square by S. Okay, but so this is in particular also implies that this is the same as saying that the probability over b bar in S to the n space, f being square full, this is low probability 2d square by S. Right, that's what you wanted to show. Note that we could have actually instead just assumed that f is square free. You don't need yes, you do not need irreducibility, actually square freeness is enough. So where did we need? So R is non-zero, degree is less than 2d square. Okay, let me keep it. So in fact we should have said that there is something stronger that we are using. Let me correct it. So the reason why this was non-zero is because the GCD of f and the derivative is 1. With respect to x. Okay, this is true if you assume f to be square free. So if f is square free with non-zero derivative, these two properties will give you the discriminant to be non-zero. That is what we used here. So if you start with these two properties, then at random fixing of y bar, you will get with high probability, you will preserve the square freeness. Okay. So thus from now on, we will make the assumption that a random projection f x comma a bar times one variable new variable t plus b bar is square free with high probability. Okay, this is because you can, if you even if you just look at t equal to 0 case, x comma b bar, f x comma b bar is square free with high probability, and so with the variability it will continue to be square free. So we can, since we are using random projections, we can assume from now on that this f at e x comma a bar t plus b bar is indeed square free. So let us then look at the version of irreducibility theorem that we will prove, or that we need to prove. So it suffices to prove the following. So let f be almost monic and irreducible. So in that case, when you randomly project, so a bar b bar from the space S to the n, then f x comma a bar t plus b bar, the chance that it is reducible okay, chance that it is reducible and square free okay. So since you started with an irreducible polynomial, you would expect that this probability will be low. Okay, probability is lower than something like this 7d6 divided by the sample space size. So, if you take the sample space slightly bigger, let us say d to the 7, okay, as 7 times d to the 7, then this probability is quite low. So, when you randomly project to this univariate a bar t plus b bar, your irreducible polynomial remains irreducible. In addition, actually this x comma b bar remains square free. Okay, you have both the properties. So, let us try to show this now. It will immediately imply the Hilbert's irreducibility theorem that was stated in the last class. So, this is a slightly technical proof in terms of notation, but the idea will be that we will try to factorize f, projected f, using Hensel lifting in two different ways. Okay, so, one way will be you look at this mod t. So, mod t, it is a univariate, there is a factorization, and then you lift it to mod t square, t4 and so on. The other way to start Hensel lifting will be that you replace a bar by the formal variables. Okay, y1, instead of a bar, use y bar, and that you look at first mod y bar, then the ideal mod y bar square, and so on. Okay, so there will be two branches of Hensel lifting, or two different ways of doing Hensel lifting. One is mod t powers, and other is mod y bar powers. So, this will be clear when we implement this idea. So, the idea is so, the idea is that this you have some information about this projection a bar t plus b bar, that f, say for example, assume that f reduces. So, from this information, how will you go to formal y bar? Okay, so that jump from fixed a bar to formal y bar, that jump will happen through Hensel lifting in two different ways. So, we will do that next. Okay. So, also for simplicity, we will assume b bar to be 0. We can assume without loss of generality that b prime is 0, just to make the notation a bit simpler, that is all. Okay, so let us do this. So, assume that, start with the assumption that f x comma a bar t is reducible and square free. Okay, so that is basically the event which we want to claim, which we are claiming in the theorem statement to be rare, low probability event. So, let us assume that event happens. So, then we do Hensel lifting mod t powers. So do Hensel lifting So when you do this, what's the first step? First step is x comma a bar t mod t factorizes into univariates in x, let's say g0x, h0x mod t. Since we have assumed x comma b bar, which is x comma 0 bar, to be square free, that is a very important property, because now you know that G0 and H0 are co-prime. Okay, so this is a co-prime factorization, and we can assume G0 to be irreducible. So let us remember that. So degree of f is degree of fx0 bar, and G0 bar is an irreducible proper factor. Co-prime to H0. Right, that's the starting point of the Hensel lifting number 1. So this will then imply that f x comma a bar t after k times will give you gkx times hkx mod t to the 2 to the k. Okay, let's call this equation 1. So this is what you get starting from G0 and then repeating this Hensel lifting k times. That's one way. Now let us do something different. Okay, so Hensel lift mod y bar powers. Okay, so what will that root give you? So f x comma y bar t what is it mod y bar? So the amazing thing here is that mod t, mod y bar, it's the same starting point. Okay, so mod t you are looking at f x comma 0 bar, and here in the new setting also mod y bar you are looking at f x comma 0 bar. So it's the same starting point. So you can use G0 as before. And then when you do Hensel lifting, what you will get is you will get let's say gk prime, which is a polynomial in everything, right? So it's a polynomial in x, in t, and in y bar, and you will get hk prime polynomial in x, t, y bar modulo what? So this is modulo y bar to a large power 2 raised to k, right? That's your endpoint of the second type of Hensel lifting. Now we ask the question, what is the relationship between 1 and 2, right? So intuitively, second Hensel lifting should be the functional version of the first Hensel lifting, right? So in the second Hensel lifting, you have this y bar hanging around. If you fix it to a bar, then intuitively it should give you equation number 1, the factorization number 1. But we don't know for sure, right? So we have to, if this is true, we have to actually prove it. Okay, so let us write one more equation which is f x comma y bar t factorizes as gk prime hk prime mod also t raised to 2 raised to k. This also follows from the above factorization, because note that y1 to yn we are multiplying each of these variables with t, right. So if you set t raised to 2 raised to k to 0, that will be like setting this y bar to monomials in y bar of degree 2 raised to k to 0. It's actually equivalent. Okay, so we actually have now we have factorization 1 and factorization 2 in the same modulus, right. We have mod t raised to 2 raised to k in both the moduli. In one we have gk hk, in the other in one we have gk, in the other we have gk prime, and in one we have a bar, in other we have y bar. Okay, that is how we read this. So what's the connection between gk and gk prime? So note that here we can invoke the uniqueness of Hensel lifting mod t raised to 2 raised to k. Okay, gk and gk prime, both of them are almost monic, and for almost monic factors there is this strong uniqueness property of Hensel lifting factorization. So we can actually invoke that. So what will that give you? So by factorizations 1 and 2 of f x comma a bar t and the uniqueness of Hensel lifting since f is almost monic, we conclude so what do we conclude? We conclude that so let me change the notation slightly to include a bar here. So, we will conclude that this gk a bar and gk prime, okay, they are the same if you fix y bar. That is what we conclude. So, gk a bar at x comma t is equal to gk prime at a bar mod t raised to 2 raised to k. Okay, that is the relationship. So, this is the crux of the proof. This is what you should understand and remember, that we factorized one in with a bar fixed mod t raised to 2 raised to k, and other was with a bar with instead of a bar using the functional version which is y bar mod t raised to 2 raised to k. We got two this fixed and the functional type of factorization, and then by uniqueness of Hansel-Lifting factorization for monic factors, we deduce that they are equal for y bar equal to a bar. Okay. So, but still we are not really done, right, because this factorization or this gk prime is happening only mod t raised to 2 raised to k. Right? What does it tell us about f? So, remember that in the original theorem statement, we have to say something about f, whether f projected being reducible implies that the original f is reducible, right. So, we have to now move to original f. So, for that let us just record that gk prime x comma t comma y bar is a potential factor of f x comma y bar t, right, but we do not know whether it actually divides f x comma y bar t exactly. So, in these situations or in this situation, we will do what we did before. So, recall the case of bivariate factoring. So, in bivariate factoring, we were in a similar situation. We had a potential factor mod ideal power, and we wanted to deduce an actual factor. So, what did we do? We solved a linear system. So, consider a linear system as done in the case of bivariate factoring. Okay, so let us move to that now. So, claim is that with high probability there exist polynomials g and Lk in all these variables x, t, y bar such that g is a multiple of Lk and Gk prime mod t raised to 2 raised to k with degree restrictions. Okay, so what is that? So for G, the degree restriction is that degree of G with respect to x is smaller than that of f. And degree of t is smaller than at most d. Okay, this is expected because, or this is natural. It's intuitive because with we hope to, just like in the case of bivariate factoring, we hope that this gk prime will be associated via multiplication, via product, associated to a factor g of f x comma y bar t. So the degree of it with respect to x should be strictly smaller, and if you look at the degree of g with respect to t and also y bar, actually it should be, it cannot exceed d. Okay, that's one thing. But for y bar it's a bit more complicated because there are many variables, right? There is y1 to yn. So let's write that down. So degree of g with respect to y bar is what? It is degree of, so I am defining the degree of g. Yeah, that's bad notation. Let me change it slightly. Let me call it d prime. Let me call it d prime, which is actually degree of g with respect to yi for all I. Just sum it up. Yeah, the intuition of this is not clear. We will see in the calculation. So we will claim that this will be at most 6d5. Okay. So that is the claim we are making. We are saying that this gk prime itself may not be dividing f x comma y bar t, but there is some multiple of it which can be found by solving a linear system, where the degrees are like this. So degree with respect to x is strictly smaller than that of f, degree with respect to t is less than equal to that of f, and the individual degrees of g with respect to yi, they sum up to this 6d5. So actually this g may still not divide f. What we will do once we have shown this claim is that we'll actually take its GCD with f, like we did in the bivariate case, and we'll show that the GCD will divide f. Okay, so this is a mysterious polynomial g. So let's prove this claim first. It is similar to what we did in bivariate, but slightly more complicated because of n being arbitrary here. So, the first thing that we will do is use this random A bar property that we had before. So, we know that we have a good fraction of A bar such that f x comma A bar t has a liftable factorization. Actually, why is that? Why is that fraction good? Let's go back. Just take a step back and try to understand this. So, what we are actually assuming is the opposite of what we want to show, that for most of the A bar B bar, f x comma A bar t plus B bar is reducible. Okay, and then because it is reducible, so you can and because x comma B bar f x comma B bar is square free, so you can Hensel lift. So that is what we are reading of. So that actually I should add here, is reducible and square free greater than equal to that much fraction for most A bars. Actually, that is what our assumption, starting assumption. So we'll actually use this part now, that for most A bar whatever we have done is actually true. So which means that for a good fraction of A bars, x comma A bar t has a liftable factorization, which implies that there exist G A bar and L k comma A bar such that G A bar x t is G k prime x t A bar times L k A bar. So, how is this happening? Well, this is just the same equation that we get by Hensel lifting, say in the second way, right. So, in the second way you got this f x comma y bar t factorizes as g k prime, and then we also showed that g k prime, in fact, when you fix y bar to A bar, it's g k A bar. So, that those properties which we have shown, we are using them now. Okay, this red equation we are now using. It's true for most A bars. Okay, and the remaining part we are just calling it L. Right, it was g k prime times h k prime, but that remaining thing we are calling now L. So this is just a reformulation. So, and you can see easily that this degree of G A bar with respect to T, right, it's at most D, because this is actually a factor univariate factor which we lifted. So the degree is bounded by D. Now on the other hand, let us make A bar formal. Yeah. So on the other hand, consider the equation g x t y bar g k prime x t y bar times, so let us remove the variables, it's disturbing, g k prime times L k mod t raised to 2 raised to k. Consider this equation in red and consider the equation above in blue. So, for the red equation, you know that if you fix y bar equal to a bar for many a bars, for in fact most of the a bars, the linear system has a solution, right. So, intuitively it should also have a solution without fixing y bar. That is the key idea. Okay, this is why we have been trying to connect y bar with a bar. So, it should have a solution as or since for most y bar fixed to a bar, the system has a solution. Okay, this idea in green is the key thing that we wanted to get at. So, we have these two linear systems, and the red one is the main one, the functional one. For it to have a solution, it is actually enough if its random fixings have a degree bounded solution. So, now all that remains is to formally prove this. So, for that we will basically convert this linear system into a matrix, and the proof will basically boil down. Right. So, let us just now implement this idea or show that this is what is actually happening. So, this linear system, how many unknowns are there? So, number of unknowns, let me first specify here that we are thinking of unknowns as polynomials or functions in y bar. Right. So, g k prime is a polynomial in x, t and y bar. We want to find g and L k. So, let us view them as bivariates, so x comma t, with the coefficients being functions or polynomials in y bar. So, in that sense, how many unknowns are there? So, that number is easy to compute. So, degree of x is what? At most d, right, and degree of t in this equation is also at most d. That is because of what you know about g k prime. and the type of G and L that you are looking for. Let me take that back. No, so for G it is D times D. It is D times D. For G, for LK, degree of X is, yeah, it is at most D, but degree of T may go up to 2 raised to K minus 1. Okay, that is the bound. This is for G and this is for LK. So then we can estimate it like as follows. Okay, I did not tell you what K is, how big K should be. So let me add that. So I will be needing it to be between D square and 2D square. Okay, I am assuming K to be something like 2 log D. Okay, so with that it's D square plus D times 2D square, which is so that is cannot exceed 3D cube. The number of unknowns in this bivariate system is at most 3D cube. So let us call this number of unknowns M. Okay. Yeah, and note that this red equation is actually a homogeneous equation. It's a homogeneous linear equation in these unknowns, right? So you get kind of this M cross M matrix. When you compare xt monomials both sides. To get constraints. Yeah, but why would it have a non-zero solution, right? So for that we will rely on the random fixing of y bar. We know that if we randomly fix y bar, then there is a solution always. So from that you can deduce that for formal y bar also there has to be a solution, because if there is none, then what happens? So if equation 3 has no solution, then the corresponding M small m cross small m matrix M so what are the entries of this matrix? Entries are coefficients of GK prime. So then this corresponding matrix M has a non-zero determinant. Right, it's a homogeneous equation. If it doesn't have a solution, non-zero solution, then this means that the matrix M is actually invertible. So if you compute its determinant, let's call it, so the matrix M has coefficients of gk prime, right, and those are all polynomials in y bar. So the determinant is also a polynomial in y bar. So that is non-zero. Its degree is given by the dimension, which is M, times each entry's degree, which in turn depends on the degree of gk prime in y bar, right, which is 2 raised to k at most. So what is M? M is at most 3d cube, and what is 2 raised to k? That is at most 2d square. So you get 6d5. So d is non-zero and it has degree at most 6d5. So the probability that it vanishes for a random fixing of y bar, that is quite small. Right. So for random a bars, also the same property will then continue. So for random a bars also there will be no non-zero solution, which you know is not the case. That is a contradiction. So this contradiction finally gives you that G and Lk exist. Degrees restrictions or degree bounds which you were claiming in the statement of claim 1, degree of G with respect to x and t is clear. It is clear because here in this equation in blue, those are the gk prime x comma t comma a bar that you had, right. So both x and t, the degree bounds you have, you continue to have. About y bar you have to deduce. So that you can deduce by as follows. So sigma degree of g yi I 1 to n, this is what? So this will really depend on the degree of the determinant, okay, because remember that you have a homogeneous linear system. So the solutions will actually, solutions of this linear system, they will actually be given by ratio of determinants. So we can safely say that all this is at most degree of the determinant of M, degree of dy bar, which is at most 65 as shown above. This is by Kramer's rule. Okay, so what we have shown is that claim 1, which says that G and Lk will exist in this restricted degree. G and Lk will exist also, and they will have restricted degree. And the hypothesis was that F is factoring for most of the y bars equal to a bar setting. Right? That is what we started with. So, if f x comma a bar t factors for most a bar, then we have shown that Hensel lifting will give you this gk prime for most a, and from that we have deduced that you will get a gk prime with formal y bar also, and from that you will get a g. So, next time what we will do is that we will just take the GCD of G with f, okay, and that will actually factor f, and factoring f means you get a contradiction. Okay, that is our you get a contradiction, or you get that f is actually reducible. Okay, so if f is reducible for most y bar equal to a bar setting, then it is actually reducible. So, reducibility implies reducibility. So, let us do this in the next lecture.